Howdy, and welcome back. Believe the lighting is sufficient. Welcome back to my lecture series on introductory astronomy, specifically for my class ASTR 103, Astronomy, Spring of 2022. This lecture is entitled Home Base, the Earth and the Moon. But before we start that, what I'd like to do is finish off from what I discussed in Lecture 8, which is the formation of planetary systems. Really, I laid the groundwork for the benchmarks needed to come up with a salient formation theory of planetary systems. Specifically, I looked at the commonalities or the characteristics of our solar system, and then through the study of exoplanets, we have increased our data. Instead of using one data point, simply our solar system, we now have many data points because we have many or multiple examples of solar systems around other stars. And we have now come up with basically the constraints or the things that need to be explained with any formation of the planetary systems. Now, the initial formation theory was developed in Nice, France. I imaginatively now referred to as the Nice theory, but it has since been augmented because of the discoveries or enlightenments, as it were, of exoplanet research. So I'm going to go over that formation mechanism. Now, again, just to review, with our solar system, a few of the benchmarks that we need to account for is that all of the planets in the system seem to orbit in the same direction, matching the rotation of the parent star. All of the orbits of the planets are fairly well constrained within the ecliptic. The planets, except for Uranus and Venus, seem to rotate in the same direction that they revolve, or otherwise a counterclockwise direction as viewed from the top, depending on as we define our coordinate system. We have planets are highly differentiated in their compositions. I'm losing my words today. Generally, we have that the heavier or the more dense material is located in the center of the planet, with lesser dense material as you move further out towards the crust. Even with gas giants, we have denser material closer in, and then lighter material further out. We also have debris surrounding, and I say that, forgive me those who study asteroids, comets, and so forth. I apologize for the derisive terminology, but we have leftover material from the formation. Or rather, we have what appears to be smaller bodies. I should correct that and say we have these smaller bodies, asteroids, comets, and the like, and they are located in particular regions of the solar system. And when we look at the asteroids, we notice that some of them appear to be differentiated, as if they were a part of a much larger body that went through the differentiation process and were ultimately broken apart. So our solar system, we need to explain those as well. And in addition to that, we need to explain why comets appear to have larger inclinations than the objects within the solar system. I hesitate the word to use inner part of the solar system, but the inner planets and the outer planets. And then you have the Oort cloud, which has a smorgasbord of eccentricities and inclinations and so forth and so on. So all of this has to be explained by any cohesive theory of solar system formation. We also, through exoplanets, realize that our solar system is not I was going to say that it's a standard, but we really can't say that at this point because of essentially selection effects with our observations. We are more prone to finding certain types of exoplanets than others. But what we can say is that there are exceptions to what our solar system looks like. One of them is we have found Jupiter-mass planets very close to their host stars, which we obviously don't see, and the Nice theory, as it stood, could not explain. So we need additional mechanisms within the Nice formula or Nice theory in order to explain these things. And I talked about those a little bit in the previous lecture. We have planetary migration. We have forces within the disk which cause planets to either move in towards the star or out away from the star. And we also have planet-planet scattering, where once the planets are formed, they may have formed fairly close to each other, and eventually, I should say on a short time scale, they will gravitationally interact with each other and, possibly eject one. They will gravitationally interact, change their orbits, and potentially expel one of those planets and create a rogue planet. So, ultimately, what is the Nice theory? What is the modern conception of planetary formation? Well, in brief, it is a condensation theory. So what we have is stars are formed in a giant molecular cloud. So you have this complex cloud of hydrogen and helium gas that is hundreds of light years, possibly even thousands of light years across. But it's not homogeneous. It has parts of the cloud are more dense than others. And so those are more prone to larger gravitational attraction. And so it pulls the gas in more so than a less dense environment. And that triggers a runaway, as it were, phenomenon where the gas gets smaller and smaller. The core of that smaller contracting, what we actually refer to as a core, that core gets smaller and smaller, and then the middle of that core, because gravity is a function of distance, the stuff in the center is going to collapse faster than the stuff that is further out, and so that forms a star. And then, because of in that same process, because of a thing called conservation of angular momentum, that cloud, as it gets smaller, will spin faster, and as a result, it will spin into a disk. And from that disk, we have various processes that we have two possibly competing theories as to how planets are built. I personally think that they are not mutually exclusive, and so it could be that certain planets are formed one way and the other mechanism forms other planets. But regardless, I will go over both methods. And so that you have these planets formed from small portions or grains of dust that are trapped located in the dust cloud, located in the collapsing disk. And they all get together because things in the universe tend to get social, and bing, bang, boom, you form planets and everything else. So what is conservation of angular momentum? Well, linear momentum is a consequence of Newton's first law. If something is in motion, then that object has a momentum, and it's going to carry that momentum as it moves forward. If you were to change that direction or change its acceleration in some way, then the total momentum of that object is conserved. So the other part of the momentum, if it changes, goes into whatever it was that caused that thing to veer off. So in a similar way, conservation of motion for a spinning object is conserved. So the classic example is figure skater. On the right, you have the bottom, you have this more physics-y equation, which is that the angular momentum is equal to the moment of inertia crossed with the angular momentum, or angular velocity of the object, or in this case, person. Because angular momentum, L, is constant or conserved, we refer to that as a constant. And then if you're talking about one point or one mass going around another mass, then the moment of inertia is mr, and then v can be approximated, or is approximated by, or omega is approximated by v. But with all that being said, simply put, if you have a distributed mass or a figure skater with their arms out, they're going to spin at a certain speed. If that figure skater brings their arms in, the mass distribution, in this case r, gets smaller. So in order for things to be conserved, because mass isn't changing, the velocity or spin has to increase. So figure skater brings their arms in, the figure skater gets faster. She brings her arms out, she gets slower. So when we talk about disks, when we talk about these cores of collapsing which form the star, you have obviously a large core that then collapses down into a smaller thing. And again, it has a certain speed when it's big, technical terms. But the speed is fairly slow. As the thing gets, as the object gets, or the core gets smaller, the mass isn't changing appreciably. And so as it gets smaller, it has to speed up. And angular momentum speeds up essentially in only one direction. It only speeds up or only affects the material that is going around in this plane. Anything in this plane is unaffected. So what that means is that a spherical distribution of material becomes more and more oblong. So the stuff at the top, again technical, just collapses down. The stuff in the middle will bulge out and will bulge out, but also get smaller, and it will get faster. And it will create what we refer to as a protoplanetary disk. This is one of the more famous of these protoplanetary disks. As an aside, I loves me some protoplanetary disks. I did my thesis work, or half my thesis work, on looking at these objects, which are known as, imaginatively enough, young stellar objects. This is HL Tauri. It was the first planetary disk that was directly imaged by interferometry. And so what we see here, and it's the first image of a protoplanetary disk where we can see the face of the disk as opposed to the edge of it. And so now we can study the formation of planets. Those rings that you see there are evacuated parts of the disk because of a gravitational mass in the disk, basically clearing out that material. So part of that material goes into the planet, making the planet, and the rest of the material just gets pushed out because, planets are bullies. So, and in the center of this disk is the star. At the moment, it is a protostar, and it's a protoplanetary disk, but ultimately it will form into a solar system. This is what I was talking about, or more a graphic of what I was talking about with conservation of angular momentum. So you have this axis of rotation, the axis via which all material goes around. And then as it gravitationally collapses over time, it spins up. Again, the stuff that is parallel to the axis of rotation just simply collapses due to gravity. And then the material on the edge, or perpendicular to the material, I really can't speak today. Will also gravitationally collapse, but it will also spin up and form this disk-like material. So what is the condensation part of the condensation theory? Before we can really talk about that, the one thing we need to talk about, or one thing we need to address, is that this disk is not homogeneous from a composition standpoint. And the reason for that is because the disk has differing temperatures. The entire disk is not one monolithic temperature. as you might expect, stuff that is near the star is hotter than stuff that is farther away from the star. And what that means is certain types of materials, depending on their melting points, will be able to survive close into the star, and then other materials will can only survive further away. We refer to these as violets, and I am completely failing on the second one. More specifically, it's just completely escaping me. On more broadly speaking, you have irons and silicate dust, rock essentially, can survive much closer into the at higher temperatures than things like water or methane or ammonia. These elements break apart at higher temperatures or at lower temperatures than iron does, for example. And so you can only find water ice and these other gases further out. You can pretty much find hydrogen helium throughout the entire disk. And to a certain extent, you can find iron and silicates to the outer part of the disk. Something else to keep in mind is that the disk is not homogeneously dense. It does not have the same density running through it. And so there is more material in the inner part of the disk than there is as you move outward in the disk. So that will also affect primarily the sizes of these objects. And before I click over, we have this line which we refer to as the snow line or ice line, as I like to call it. And that line is where in the disk the temperature is such that water ice can exist without sublimating. Sorry about that. And if you thought that I was being rude, I get robocalls all the time. Anyway, so we have a snow line or an ice line, and again, what that means is that that is the point at which water ice can exist. If water were to exist closer to the star in the hotter region of the disk, it can only survive as water vapor. If it's in the outer part of the disk, it can survive as ice. And that's going to again affect the compositions of the planets that we see. If you remember to a BACA lecture, you might start putting things together remember, if you have the Jovian planets, you have the two gas giants, and then you have the two ice giants. Hopefully you can see that the two are correlated. Now, how does this come into effect? So we have this model called core accretion, or let me take a step back. This is actually core accretion and gravitational instability pretty much start out the same way. What we have is a cloud of material, gas and dust. The dust grains and the ice grains, or ice crystals, they are typically magnetic. They are typically electrically charged, and because of that, some of them will attract to each other. Think of this as static electricity. Static electricity makes things come together. So through static electricity, these smaller dust grains will attract each other and smack into each other, and they'll get larger and larger until around, I believe it is around 10 meters or so, the object will lose most of its charge and will become large enough that the strength of gravity can replace that attractive force. Now the traction of mass, or the building up of larger masses, is due to gravity, and so this thing becomes larger and larger. And then we have objects that are around 100 meters or so across, and we refer to those as planetesimal. And we get many millions of planetesimals in the very, very beginning. And then these objects will smash into each other. And ultimately, you have three fates for these planetesimals. If you can get up enough mass quickly enough and become a larger planetesimal, gravitationally speaking, when gravitational attraction happens, you literally have rocks smashing into each other. Depending on the mass of the two objects and the speeds of the two objects, either the objects will smash, get hot, and merge, or they will slam into each other, get hot, and break apart. So, depending on whether or not you can, if you're a particular planetesimal and you are lucky enough that everything that's building you is fairly low energy, meaning that they are traveling fairly slow and you can build yourself up rather than break apart, you become a planetary core, either a terrestrial planet or the cores of gas and ice giants. If you are unlucky, then you will try to form, and then something will come by really high speed and smash you to bits. Or you can just be lonely, and there's just not enough material to actually form, to really get that material to really even form large planetesimals, as it were. And so that explains why we have planets versus why we have comets and asteroids. In a way, comets and asteroids, and again, if you study these things, I apologize for the derisiveness of this, but these are ultimately failed planets. These are objects that either broke apart into smaller objects and never were able to coalesce, or they never coalesced in the first place. And when we talk about objects that never coalesced in the first place, primarily we're talking about things in the Kuiper Belt and the Oort cloud, because again, there's a lot of space out there, and there's not a lot of, so the density of the material is much less. Because they're a large space, the distances between objects is very large, and so the forces that bring these things together are fairly weak, and given the time scale of the formation of the solar system, they simply just do not have enough time to build up to larger and larger objects. That is not exclusively the case, because there are dwarf planets out there, and the number of dwarf planets is not well known at this point. But for the majority of, we can say for the majority of these objects, they are small comets and so forth. Now, when it comes to the formation of giant planets, you have core accretion, and then you have hydrodynamic instability. Core accretion is, as I described, you have the rocky core forms first by the electrostatic and gravitational accretion, and then the gases of the atmosphere and the ices, which are trapped in the atmospheres, they are brought together by gravity. The hydrodynamic instability model basically says that the giant planets form similar to stars, where you have high density material in the parts of the disk actually are not homogeneous. So if you were to look at, say, an orbit or a radius away from the star, along that radius, it's not equally dense, and so there are parts that will come together faster than other parts, and through this, the giant planets are formed. Now, each of these ways has, as I said, they better explain. So, like I said, core accretion is better to explain terrestrial planets. Hydrodynamic instability explains giant planets. The main problem with choosing one over the other is really a matter of time scale. We know that these planetary systems typically form on the order of tens of millions of years. So depending on the model, in order to get some of these planets to form at the outer parts, the model just predicts these. It's just too long. The time scale of the model to do the work, or the methods within a model to do the work, are just too slow. And so you have two examples. The core accretion, you have, as I said, the planetesimals coalesce, and then rocky cores form, and then bing, bang, boom, you have planets. Here with core accretion, and then gas accretes onto the core, and then you have a big giant planet. Now, bing bang boom, you have a planet. And most of the disk is gone at this point. So this is a fairly long time scale process. Again, depending on how far you're out. If you are in the inner parts, it's not quite as long a process as if you're in the outer parts. So because of that discrepancy, the hydrodynamic instability model has come up. And here you have gas in, like I said, part of the disk coalesces due to higher density, meaning that a stronger gravitational attraction. It quickly builds up the core and surrounding gas, and this happens. This process is far quicker, and so it can explain why we have gas giants forming in the same time frame as terrestrial planets. And then you have the evolution of planetary systems. This is the part of the original Nice model that wasn't quite thorough, that wasn't quite accurate. And like I said, through gravitational interactions, either planetary migration or scattering, you can change essentially the morphology or the shape or the appearance of these stellar systems. Again, the example that I gave was larger mass planets, very, very closer in. And as I said, the Oort cloud and the asteroid belt, the Oort cloud and the Kuiper belt, they can evolve again. Primarily the Kuiper belt or the Oort cloud objects, which formed first, form first, and so they've been around the longest. They have a larger chance of smacking it or gravitationally pushing each other around and either ejecting the material or more than likely causing very high elliptical orbits. So now, getting to the title of the actual lecture, let's talk about the Earth and Moon. The Earth and Moon system is pretty much unique. Unique in the sense, and this lecture brought to you by Wendy's. It's unique in the sense that no other planetary system has a moon of comparable size to the host planet. While Jupiter has larger moons than our moon, those moons are tiny in comparison to the size of Jupiter. And this has consequences on the sort of survivability of the Earth, and it affects the evolution of the Earth. And we can see these effects on the Earth's climate through fossils of prehistoric animals, particularly those found in Antarctica, the Arctic, and I suppose the Antarctica as well. So what makes the Earth unique? Well, like I said, the Earth-Moon system unique. Well, not only do we have the relative size comparison, but the Earth is the only body where liquid water exists to any real significant extent. And in fact, the majority of the Earth is covered in water, roughly around 71%, although I'm sure due to climate change that's actually getting larger. And the atmosphere is such that it is made up of the proper constituents, and it's not thick, that it can support a complex biosystem. Biosphere. You can have life develop and flourish, given the atmospheric composition and temperature and so forth and so on. And as I said, the moon will affect the Earth's evolution. The two primary ways that it does this is that it slows down the Earth very minutely over time, or at least from a terrestrial standpoint, from a standpoint you and I, it's very, very small, almost negligible. And then we have that is not the reason for leap days. And then and probably more importantly, is it stabilizes our climate. Now let's take the Mars, for example. Mars and the Earth have similar axial tilts. That's coincidental. The moon or the Mars, so the axial tilt of the Earth actually varies by about 2 degrees, give or take. The axial tilt of Mars changes by about 60 degrees. Now, the reason for that is Mars does not have an appreciably massive moon to basically just keep the Earth stable, to keep Mars stable. Without that moon, the axial tilt is free to move at a much higher angle, or much larger angle. And you can imagine that radically changes the climate, because seasons are dictated by the axial tilt. If you have an axial tilt that is 0, then you essentially have no change in climate. You have no seasons. Your climate is simply dictated by latitude. Because the Earth is tilted, the part of the Earth that is close or is pointed towards the sun will experience summer. The part that's further away will experience summer, or winter rather. So that's why Australians celebrate Christmas on the beach. So if your axial tilt varies wildly, like Mars's does, then your difference in seasons becomes far greater. The more the axial tilt, or the larger the axial tilt becomes, the larger the difference between summers and winters. Summers become progressively hotter, winters become progressively cooler as you, over a larger area, as the axial tilt gets larger. So, because the moon is massive, because the moon has a mass, I wouldn't say similar, but it has a large mass in comparison to the Earth. It has enough gravitational oomph to keep the Earth's axial tilt stabilized. Again, this is a graphic to illustrate the point. The moon is obviously not the largest satellite in space or in the solar system. In fact, Ganymede, Callisto, and Europa are larger. Titan is larger. The moon is comparable to the size of Io. Ganymede and Callisto are larger. The moon is of comparable size to Io, and then Europa is slightly smaller. And then the moon is obviously much larger than Charon. In a way, the moon is, when it comes to planets, the moon and Pluto are roughly the same size, which is another sort of motivation for why Pluto was demoted by everyone else but me. I think that's a silly reason to demote poor little Pluto, because as you can see, Pluto loves us. So, I've talked about the time scales of evolution. Talked about the fact that the protoplanetary disks will last for millions of years. We know this because we've looked at a large sample of protoplanetary or protoplanets and protostars and their disks, and we can, through the chemical compositions of the protostars, we can determine the ages. And so, if you have a protostar with a very thick disk, and we found that the age of that star is fairly short, and then as you get to thinner disks or very, very weak disks, the age of those the age of those stars is older. And like I said, it's around 15 million years. Now, how do we go about determining the age of the Earth so we can better understand its evolution, not only through the formation process, but along its lifetime and to the present day? And we do this through a process called radiometric dating. And this is a process by which we measure the amount of a radioactive element in comparison to what that element ultimately turns into because of radioactive decay. Radioactive elements, certain radioactive elements will decay into a different element. Radioactive uranium will turn into lead over a certain amount of time. And you may have possibly heard of carbon dating. Now, carbon dating is radiometric dating. The only problem with carbon dating is that its usefulness because of the short turnaround of the change of carbon into its daughter element, is fairly quick. It's around 5,000 years or so. So it's really only useful out to tell the age of about 50,000 years, or really the time span of human existence. If you want to look at rocks, primarily you want to use uranium. And by looking at different structures, or looking at different rocks in the Earth's crust, you can determine how long ago that crust was created. And we've determined that the Earth's age is around 4.5 million years old. And one of the other reasons why we can, or one of the ways that we confirm that, is by looking at meteorites. Well, one, we look at meteorites which we believe came from the moon, and we have moon rocks because we sent people up there to basically steal them. And so we bring the moon rocks down, and we can radiometrically date the moon rocks, and we find that like I said, they match up very well, about 4.55 billion years or so. So an atom is something of a particular element which is characterized by a number of protons in it. If you remember from a couple lectures back, I described the atom as the nucleus of an atom is made up of positively charged protons and a mix of negatively or neutrally charged neutrons surrounded by negatively charged electrons. An isotope is a particular type of a same element. So it is, for example, uranium, and then you have an isotope of uranium. That isotope has a different number of neutrons. And so isotopes of elements will undergo what we refer to as radioactive decay. The one process is that the neutron changes into electrons, and so we have beta decay, and beta decay, and it changes again. Uranium changes into lead. But the radioactive decay of any particular atom is random, and so that is not useful for us. We cannot use that to actually determine the age of things. However, if you have a large number of identical atoms, the approximate age, or the average age of the decay, is something that we can predict, and that is what we refer to as a half-life. A half-life is the time scale of, you have 100% of what we refer to as the parent rock, the parent atom. So you have a rock composed of the parent atom, and then you have a half-life is how long it takes to get that rock to have half of that parent atom. Another half-life, so if the half-life is 5,000 years, or if the half-life is, say, 1,000 years, then the half of the parent atom, or half of the parent atoms will go away. They will change into what we refer to as daughter elements. And then another 1,000 years, that half will turn into a fourth, another an eighth, and so forth and so on, as you can see from the elapsed time. And if we can measure the fractions of, say, of uranium as a function of iron, for example, then we can, and using the time scale or the half-life of uranium, we can then basically determine the age of that object. So T in this case is the half-life, F is the fraction. So it's a fairly simple calculation. It is more complex in practice. So the inside of the Earth. What can we say about the inside of the Earth? Well, let me start off by saying that this is theoretical, and my best friend is a geologist, and he looks at this and kind of balks. This is a gross simplification of what the interior of the Earth looks like. As with pretty much everything in nature, the nature is far more interesting and complex. But to first order, or to the order of a spherical cow. This is what the Earth looks like. We have a crust that is about 5 to 60 kilometers thick. Under that, we have a mantle. The crust is made up of silicate rocks. The mantle is also made up of silicate rocks. It's at a higher temperature and higher density, higher pressure. That's roughly around 3,000 Kelvin, or 3,000 kilometers in thickness. You then move into the outer core, which is a molten mixture of iron and nickel, which spins in relation to an inner core, which is solid iron and nickel, mostly iron. And so that's basically the interior of the planet. If you remember that process called differentiation that I talked about, this is a great example of it. Iron is far more dense than silicate rocks. For example, aluminum or aluminium for all of you Brits out there. And so you're going to find the vast majority of iron in the core of the Earth as opposed to finding it on the crust. And you're going to find the vast majority of aluminum on the crust than you are going to find in the core or inner regions of the Earth. Now, the mantle, the liquid hot, is filled with liquid hot magma, or it's semi-fluid, I should say. And because of how energy is transported and because of the physical conditions within the mantle, specifically its density, you have convection as the primary way that energy is transported from point A to point B. As you might imagine, the temperature gets hotter as you get to the inner part of the planet, and that's primarily due to the fact that the material is under far higher pressure on the inner part of the core than it is on the outer part of the planet. And so, in the mantle, you have these convective cells. You have this collection of material which starts off roughly at the same temperature, and then it will literally rise through the mantle, pushing away everything else. And as it does so, it will cool off and supply energy to higher and higher levels of the mantle. And again, as it loses energy, the amount that it can supply to the surroundings is less, and so you get this temperature gradient as you move through. But more importantly, you have these convective cells can actually cause the Earth to change. If the convective cells work against each other, we can have new crust form. The crust actually splits open, the magma comes up, cools off fairly rapidly due to the ocean water, and you have new crust. Or you can have a process called sublimation where the crust, I should have started off with the fact that the crust is thin enough that these convective cells, the action of these convective cells, can actually break the crust apart into what we now refer to as continental plates or tectonic plates. And these continental cells can actually move these plates around. They can either slam them, you can either pull them apart, creating more crust, or you can slam them into each other, and where one crust actually goes beneath the other crust, and the other crust gets built up into higher, basically, mountains. And the Himalayas are a great example of this. The Indian subcontinent is slamming into the Asian subcontinent, the Euro-Asian plate, and there's a tremendous amount of subduction, and that's why the Himalayas are so freaking huge. Now, you might ask, how do we know? As I said, it's a model, but how do we know how the Earth is differentiated? Why do we know that more specifically, why do we know that the mantle is semi-fluid? Why do we know that the outer core is more fluid, and then you have the solid inner core? That's because we have earthquakes. Earthquakes are a thing. Because Bruce Willis and Ben Affleck have not been able to drill down any further than 12 kilometers, we have to use some other method, and that's That's seismic waves or earthquakes. And if you get that reference, then either you're old or you like classic cinema. And when an earthquake pops off, it does so, and it creates these seismic waves. Think of it as dropping a rock into a puddle. In that sense, it creates the rock in the water. The water will create S waves. But earthquakes, because the medium is rock, will produce two different types of waves. We have S waves, or shear waves, and then we have, or secondary waves, depending on how you want to look at it. And then we have P waves, or primary waves, or pressure waves. S waves are what we refer to as transverse. They go up and down. And then we have P waves are compressions. They're kind of like a slinky. Oh, I have a slinky. Sweet. So, pressure waves are... That is a really bad example. But anyway, so much for the slinky analogy. You have parts of as the wave propagates through the rock, parts of the rock become denser and parts of the rock become more rarefied. And because we have seismographs all over the Earth, we can record the amplitudes and types of these waves as they pass through the crust. So this basically just summarizes what I've just talked about with primary and secondary waves. Key component here is that primary waves can pass through solid and liquid matter, whereas S waves can pass through solid and semi-liquid, semi-fluid matter. And both waves experience refraction, meaning that as the wave passes through a medium of denser or of changing density, it's going to bend. Now remember, the density changes as you move through the Earth from the crust to the core. Depending on the medium, depending on if it's solid or liquid, that density is going to change in a different way. Again, it's going to increase as it gets down, but the density is going to be far less. I think that's right, far less, and so the amount of curvature is going to be more drastic. I probably have that wrong. I apologize for that. I should look that up and put that in the comments if I am wrong. Or the description. Anyway, take-home point is P waves can travel through the entire Earth, but depending on depending on what medium they're traveling through, they will bend in different ways. So, for example, we have a P wave you can look at the top. You have the P waves will propagate out from the earthquake and go through the mantle, and you'll have a region where the P waves are found. And then as you change, the angle becomes more and more inclined towards this core. The P wave will actually pass through onto the inner part of the core, which is liquid. The P wave will refract even more, and then pass out of the beyond the outer core, back into the mantle, out to the crust, and you get this weird shadow where there are no P waves at all, and then you have P waves pick up again, and you can find them on the opposite side of the planet. S waves cannot pass through liquid material. They basically will stop once they hit liquid material. So you'll only have S waves found over approximately half of the Earth. That is where the earthquake originated. You do not find S waves on the other side. And so given this data, given where you can find P waves and given where you can find S waves, you can then begin to model what the interior of the Earth looks like, both in terms of density and also in terms of phase, of whether or not it's rocky, semi-fluid, or liquid. Speaking of the Earth's crust, as I said, the Earth's crust is thin enough, or the lithosphere technically, is thin enough that the convective action of the molten core or the molten mantle, semi-liquid mantle, will cause the planet's crust to crack, and we have what is known as tectonic plates. For example, we have the North American plate, you have the Eurasian plate, the African plate, so forth and so on. These plates are all moving in differing directions. As I said, the Indian plate is smashing directly into actually I got that backwards. The Eurasian plate is smashing directly into the Indian plate, which is then directly smashing it into the African plate. But you can also have sideways action, where the Pacific plate is actually moving along, not towards or away, but along the North American plate. And you can have shifting in that direction. This is the reason why living in LA is a bad idea. Well, at least one of the many reasons why living in LA is a bad idea is you have LA is built on a fault line, the San Andreas fault, famously enough. And what happens is that this shifting is not constant. Because friction is a thing, you have the plates will try to move but stay still, but that means the pressure is continually building, and then snap, you have the two plates move with respect to each other. You'll have intermittent shifting as the pressure continues to build. You'll have minor releases of that, which is what creates the smaller earthquakes, and then the pressure is so large that it will cause a massive earthquake, and that's why people in LA are going to be unhappy when the big one shows up. Just to remind you, you have convective action causes the creation of material, particularly in the seabeds, and you'll have the Marianas Trench, for example, is created by these convective action. It splits apart the atom. It splits apart the crust, and new crust forms at the base of the trench, and so forth and so on. You have sublimation again, where one plate goes under the other, and that builds up larger. The crust gets built up more, forming mountains. You have another type of motion, and this is why we have we can thank this for why we have the beautiful islands of Hawaii. What we have is that a plate is not, again, homogeneous. Parts of the plate on the lithosphere or crust is thinner than other plates. And then also the amount of pressure building up is not as equalized as over time. And so what you have is you have this hot mantle plume, and as the plate moves, again, in not really a regular velocity, it will break open. It'll break through the crust, and then create create an island. It'll basically blow up. It will create this sort of volcano-shaped landmass, because it's literally a volcano. And then the plate will move, and you'll have a thicker part of the lithosphere over the mantle. The mantle plume does not have the pressure to break through it. Then as the plate moves, the lithosphere will get smaller, and then it will break open again, and it will create this island chain. Now, because erosion is a thing, we can determine the oldest to youngest by their heights. The oldest mountains, or the oldest islands, are the ones with the lower topography, meaning that erosion has had a longer time to work on the island, and it gets smaller. So the youngest islands, the main island, for example, is the youngest island of the Hawaii island chain. And this is why the volcanoes, or the volcanic action on these islands, is much higher. And so you only really have volcanic action on the younger islands as opposed to the older ones. So let's go above the Earth's surface. So we talked about the Earth's crust, we talked about all the stuff that's beneath the Earth's crust, or at least the major portions of it. Now let's talk about what's above the Earth's crust, the atmosphere. The Earth's atmosphere is primarily composed of nitrogen and oxygen, and then you have argon as the next leading constituent, and then you have less than 1% of the atmosphere is composed of everything else in the atmosphere. Carbon dioxide, for example, water vapor, so forth and so on. You also have ozone, which is ozone and methane, which are more complex atoms built up of smaller elements. Ozone is O3, so you have three oxygen. Components. Methane is a hydrocarbon that's composed primarily of carbon and hydrogen, and so forth and so on. And so the composition of this atmosphere creates different zones. And if you're a weather nerd, you probably know what these zones are. You have the troposphere near the Earth's crust, which is around 20 kilometers high. All weather, rain, snow, sleet, what have you, all of it is trapped within the troposphere. So canonically, let me step forward a little bit. The edge of the atmosphere is very difficult to define because the atmosphere just gets less and less dense as you move away from the Earth. And so there's no physical motivation, as it were, to basically say, yeah, this density is where the atmosphere ends as opposed to this density. I suppose you can get to the point where the density of the gas is essentially the density of space that you can find between the Earth and Mars, but it's a difficult way to determine this. So we've canonically referred to the edge of the atmosphere as the Kármán line, or around 100 kilometers. Now, if you remember with Branson and Bezos and so forth, they were going back and forth. They were, doing measurements of who got higher and whether or not they actually got into space and so forth and so on. So there are actually, the canonical one is 100. NASA, I believe, has claimed that the atmosphere effectively ends at around 80 kilometers. So there you have it. My point is, given an atmosphere that is 100 kilometers in size, only a fifth of it is where all the weather comes from. Hurricanes, tornadoes, and all that kind of good stuff. And what we find is that you have, because of the constituents, the density and the temperatures, you have basically inversion zones. The troposphere actually the temperature will decrease as you get to higher atmospheres. You should all be familiar with that. As you go to higher mountaintops, it gets colder. Hence why mountains are snow-capped. But once you get into the stratosphere, where the ozone layer is located, you actually have a temperature inversion, where the higher the atmosphere, the higher the altitude, the higher the temperature. And this is primarily due to ultraviolet rays, which ozone blocks. The higher up you get, so you have these fairly high energy ultraviolet rays coming down, and then you have this ozone layer. And these, as I said, the the ultraviolet rays are energetic, meaning that when they smash into things in the atmosphere, they cause the atmosphere's temperature to rise. When they hit the top of the atmosphere, and this also explains the temperature inversion between the stratosphere and the next layer up, you have the mesosphere. The gamma rays smack into the stratosphere. Their ozone really likes I keep saying gamma. Ozone really likes ultraviolet light, so it's going to absorb that. And then as you have thicker and thicker ozone, you have more and more absorption of ultraviolet, and you have less ultraviolet to smack things around, cause the temperature to go up. And so the temperature, if you look at it another way, actually decreases with altitude, because more and more of that ultraviolet light is being extinguish. The mesosphere, you have, this is more of a density reason for why the temperature goes down as you go higher up, and then you flip over and you get to the ionosphere, and that's basically very rarefied gas. And technically speaking, there is another layer of the atmosphere called the exosphere, which is primarily composed of electrons. You might have read a few months ago that we have detected substantial amounts of electrons going past the moon's orbit. So depending on how you want to characterize things, the Earth's atmosphere actually incorporates or actually includes the moon. But again, we're talking very rarefied. We're just talking about a few electrons per cubic centimeter. You wouldn't be able to notice if you were there. So yeah, we have upper layers, as I said, because of the warming effects, you have less warming effects as you get higher, and therefore the temperature drops with altitude. And then you get to the ionosphere, because the ionosphere is high enough up that it's pretty much exposed to solar radiation. The most solar radiation, that's the reason why the temperature spikes or rises very, very quickly. Now, thermal velocity is what we refer to. Thermal velocity is what we refer to as the velocity of particles that move due to temperature. So, particles will slam into, photons of a certain energy will slam into particles. That will cause the particle to have more energy, specifically more kinetic energy, which is the energy of motion. And then that particle will move faster, and then that is akin to temperature. So we can relate the velocity of the particle to the temperature of the object using that fairly simple equation. And hopefully you can imagine from our discussion of Newton's second law, force equals ma. The larger the more massive the particle, the smaller the acceleration if you have a comparable force. And so what that means is that given the same amount of energy slamming into a particle, if it's more massive, its velocity is going to go down, or its velocity is going to be lower than a particle with less massive. So hydrogen, or for example, given the set amount of energy smacking into it, will move much faster than, say, oxygen. Now, this is important in terms of atmospheric loss. So, if you look at the escape velocity as a function of the gravitational attraction, you can rewrite this equation, and basically you have an escape velocity. What is the what speed is necessary in order for the particle to leave? And you compare the thermal velocity to this escape velocity. If the thermal velocity is higher, then you can escape the gravitational pull. You can actually move outward. So this is the escape velocity is given by this equation in terms of Earth values. If you're looking at the Earth, m is 1, r is 1, that reduces to 1, and you're left with that the escape velocity of the Earth is 11.2 kilometers per second, which reminds me, I think I said 11.7 in an earlier lecture. I apologize if I did. So, if the velocity of the particle or the velocity of the atom is higher than 11.2 kilometers per second, it goes bye-bye. And so you can lose the atmosphere over time. If the majority of the atoms are moving faster than the escape velocity, then they go bye-bye very, very quickly, and we lose that constituent of the atmosphere. The terrestrial planets have what we refer to as a secondary atmosphere. The primary atmosphere was primarily composed of hydrogen and helium because the disk is primarily composed of hydrogen and helium. But hydrogen and helium have very small masses, and so given the temperature of the disk at that point, or at that place, the escape velocity was high enough to basically escape, and almost all of the hydrogen and helium went bye-bye. The nitrogen and the oxygen stuck around because they are fatter and slower. And also, we had more oxygen and nitrogen supplied to the atmosphere because of things like volcanic eruptions, what we refer to as outgassing. So, we also have additional elements. Our composition is different than the initial composition of the disk via, like I said, outgassing and collisions with comets and planetesimals. And then we have the great oxygenation event. We have the formation of we have plants, and so plants, because of photosynthesis, will take the carbon dioxide out of the atmosphere and replace it with oxygen. Funny enough, the first, what we refer to as a mass extinction event, happened because of plants. They radically changed the atmospheric composition, and so all of the previous life that isn't plants, they got used to hanging around in a carbon dioxide environment, and then that went away, and so they went away. That brings us to the greenhouse effect. Greenhouse effect is an effect. The greenhouse effect happens because the atmosphere is not as transparent in some wavelengths as into others. If going back to the discussion on telescopes, and particularly the lecture activity that we did in class, you know that the transparency of the atmosphere, or the opacity rather, changes depending on what wavelength you're looking at. Thankfully, the Earth's atmosphere is opaque to high energy radiation, gamma and X-ray. It is pretty much transparent to visible light, and then when you get into the infrared, a lot of the infrared region is opaque, and so when you get light from the sun smacking into the Earth, specifically visible light, it passes through and it smacks into the crust, and it warms the crust. The energy of the photons in the visible light go into the Earth and cause it to warm up. The Earth then radiates that energy as if it's a black body, and so because the Earth is only around 273 Kelvin, that means that most of the energy that it gets re-radiated is in the form of infrared light. Now, some of that infrared radiation escapes because of the transparency, and other wavelengths get trapped. And this is also affected by the relevant contributions of greenhouse gases. Certain gases like carbon dioxide, methane, ozone, so forth and so on, are essentially will absorb the outgoing infrared radiation and reflect or re-emit it back towards the Earth. Fun piece of trivia: the biggest, the element which, or molecule actually, the gas which has the largest effect on the greenhouse is water vapor, not carbon dioxide. But because water vapor occurs naturally, it does not relate to climate change, which I'll talk about in a moment. And so we have, this is just basically going over what I was just rambling about. You have, like I said, visible light coming in, depositing energy into the Earth. The Earth re-radiates that. That then, part of the infrared light gets trapped by the atmosphere and warms the planet. Now, if we're just talking about natural phenomenon, the Earth has a way of regulating the temperature of the Earth by regulating the amount of greenhouse gases that are in it. And so, as you can see, this is recent history, for hundreds of years, this process has gone along, and we have a fairly constant temperature as we go through time. Obviously, there are fluctuations, but overall, the temperature pretty much stays the same. Until we got to the Industrial Age. Once we got to the Industrial Revolution, because we switched from a wood-based fuel consumption to carbon or to coal-based fuel consumption or petroleum-based fuel consumption later on, we produced a whole lot more carbon dioxide than we were prior. And because we are dumping so much more carbon dioxide into the atmosphere, the Earth can't regulate it. We have busted the Earth's thermostat, as it were. And so we have climate change due to human activity because the temperature, because the amount of greenhouse gases that we produce, carbon dioxide, methane, so forth, that hasn't drastically increased faster than the Earth can get rid of it. And so the temperature of the globe is drastically increasing, and hopefully it's not going to. Hopefully we are not to the point of no return, and we can actually do something about it. Again, now the greenhouse effect itself is good. We need the greenhouse effect, because if the greenhouse effect were not a thing, then the Earth would be too cold to support life. The Earth's atmosphere actually warms up the Earth about 10 degrees Fahrenheit, which allows for our biosphere to exist, at least in the way that we see it. So, greenhouse effect by itself, groovy. But a higher greenhouse effect, not so groovy. It causes the Earth to warm up to an extent that the biosphere, as we see it, cannot survive. We have drastic changes in the amount of water that the water transitions from ice to ocean water, and we have rising tides. We have rising sea levels. We have potentially we definitely have more storms and possibly more severe storms and a whole host of other changes due to the climate. And we can see this again with ice melt. We can see this this is the Yosemite Glacier. This is the Glacier National Park, I want to say. Anyway, in 2002 you had this big glacier, and then in 2011, at the same time of year, this is what was left of it. So obviously glaciers will get larger and recede due to natural climate change, natural changes of seasons, but during the same time periods, you would expect that the amount of glacier that you see would remain relatively constant, because the climate is relatively constant, assuming you don't have anthropomorphic climate change. 2002, that glacier would get to that size, and you can see tiny little people right next to it. And then in 2011, not so much ice. All of that ice went into liquid water, and you can see in the upper, not a lot of liquid water in comparison to 2011. Now, this lecture is getting a bit long, but I will carry on more rapidly. Because of the fact that, as I mentioned earlier, the outer core of the Earth is liquid and it is rotating faster than the inner core of the Earth, that generates a magnetic field. That is what we refer to as a magnetic dynamo effect. To first order, to the spherical cow order, we can approximate the Earth's magnetic field as a bar magnet. Right now, the north magnetic pole is at the south, the southern magnetic pole is at the north, hence why compasses will point north towards the south, because north attracts, opposites attracts. North pole will attract the south pole, and so forth. On top of localized variations in magnetic fields, we have a much larger effect that occurs over a much longer time scale. That's not exactly well known, as far as I know. We have the dynamo effect changes. We have the fact that the Earth will reverse in polarity.
Now it is north to the bottom, south near the top. After a while, it's going to change to north at the top, south at the bottom. The way we know this is because magnetic fields can get frozen in certain rocks, like iron, for example. You can see this phenomenon terrestrially. If you have a powerful magnet, take a fork, put it on the magnet, wait an hour, take the fork off, and you can stick it to your fridge. The magnetic field of the magnet got frozen onto the into the fork, and you can stick it upon your fridge. Because of the composition of the fork, it won't last long. It will eventually become demagnetized. But there are certain elements like iron and nickel which will hold on, ferromagnetic material, which will hold on to that magnetic field for a very long time. And so certain material, we have this south-north orientation, and so some other material, we find the north-south poles. Magnetic field is good because of the thing that it produces, the magnetosphere. That is a force field, essentially. The sun is producing a whole lot of radiation. Most of it's in the visible range, but again, as I keep liking to harp on it, you have ultraviolet and gamma rays and so forth. But along on top of that, you have highly energized particles, electrons and protons and so forth like that. You have these energetic particles which, if left unchecked, would smash into the atmosphere and radically change its composition, and hence our biosphere would either end or would not appear in the same way that we see it today. And so the magnetosphere redirects these positively and negatively charged particles away from the Earth, and so it's a force field that protects us from those damaging particles. And hey, that's it. That is the end of this lecture, and so I will bid you adieu. Next time we will talk about the composition of the moon, and then we'll move out to talk about further objects in the solar system. I hope you've enjoyed this lecture and found it informative. And I will talk to you next time. Peace out.